Alright, so section 7.3, we're in, we want to learn how to solve systems of linear equations with more than two variables, okay? So we've only done like x's and y's before. Now we're adding z to the mix. So these are like three-dimensional equations. But the good news is we don't have to plot those.
We don't have to use the third axis?
No.
That's great.
Yeah, you don't really have to think about the coordinate system like that. You'll have to do that in calculus. That pain is coming, I promise you.
Oh, I remember these.
I think it's Calc 3. Calc 3 was where there was so much three-dimensional stuff. So anyway, let's look at the first example, okay, which uses the what we call the row-echelon form and back substitution. All right, and I think it's easiest to just kind of go through an example first so you can see how that works. So we've got three equations with x, y, and z in it. All right, and if you look up above example number 1, you'll see that the three equations are listed in that first section there, x minus 2y plus 3z, and then negative x plus 3y and all that. But I'm gonna teach you how to modify those equations so that you put them in what we call row echelon form, which is the next set of equations down. So where you've just got y plus 4z equals 7, and then the last equation is z equals 2. Okay? So you're basically going to solve for one of the variables in one of the equations so that all the other variables go away, and you're going to have one variable go away in one of the other equations, and then you'll be able to kind of substitute in and figure out what all the values are. But this one here starts with us already having it in row echelon form. So let's just show that, do that one first, which will teach us how to do the back substitution, which is exactly what we did in the last section. We had back substitution in that. But this is all that it means. This is pretty, I don't know why I put the z way over there. Should line those up. When you write this down in row echelon form, you should line up your variables so that it's clear. All the z variables are here, all the y variables are here, all the x variables are here. So this is how row echelon form looks. You'll have one equation where you've solved for a variable. So it's only got one variable in it. You'll have another equation that's got two variables in it, and then you'll have this third equation that's got all three. And when you line them up, it'll be like this kind of stair-step look, right? That's what you're expecting to see. And so then solving for this, you just back substitute just like we did in the last section. So now I know that z is equal to 2. I'm going to take that and I'm going to plug that into this equation, right? And I can solve for y. So if I say that y, then I can rearrange that equation and say if y plus 4z equals 7, then that means that y equals 7 minus 4z, right? And so if I know that z is 2, then that means that y equals 7 minus 8, so y is going to be negative 1. Right? And then for that top equation there, I can rearrange this guy and say x is equal to 9 plus 2y minus 3z, and plugging in all the values that I've now calculated for z and y, 9 plus 2 times negative 1, minus 3 times 2, and so that's going to be 9 minus 2, which is 7, minus 6, so this is going to be 1. And so we calculated the value for x to be 1, the value for y to be negative 1, and the value for z to be 2. And then the way that you would write your solution is you would use an ordered triplet, is what we call this, ordered triple. And that should make sense to you because when we have like the x and y coordinates and we write those in parentheses with one number comma the other number, we call that an ordered pair. Well, this is 3 numbers, so it's an ordered triple. Okay, so we put our x value first, which is 1, put our y value next, which is negative 1, and we put our z value last, which is 2. This would actually be my solution to that problem. You have a question?
No, I was just thinking we should call it ordered trio instead.
Ordered trio, okay, all right.
Just change
Yeah,
things
right.
and that.
Kind of sounds like a musical group, maybe. I'm going to talk to a couple of guys and see if we can start that up. The ordered trio, guys. This would be, for a nerd band, this would be a great name for a 3-member band, the Ordered Triple. I was in a 3-member band.
What'd you play?
Huh? I played bass and sang. I started off with rhythm guitar, and then we lost our bass player, so I switched. Huh?
You sing?
Dude, I have a beautiful voice.
Can you sing us
Is
some
that
jazz
Stevens?
lessons?
You know what?
Just make a math song.
Oh, yeah.
Maybe I'll do that. I've done that in chemistry before. We're
Seriously?
learning chemistry song. So
What?
I'll have to think about that. All right, but this would be an awesome name for a nerd band. I love that. I could wear like my chemistry lab coat in the, you know. Oh, it would be a big hit. A big hit. All right. So does everybody understand how this triple works though?
Yeah.
The order you put that in. Okay. So now we just need to figure out how do I transform my original three equations to make them look like this. So that's kind of the next part. All right.
So basically, what we did is we just found z, and then we plugged it into the equation where y is. We made the equation equal to y, and then solved it 2 in the place of z. And
Yeah.
we did the exact same thing for x. We set it equal to x, and then plugged in y and z, and got the answer.
Yeah. So you start at the bottom, plug this stuff in here,
Yeah.
right, and then you'll solve that, and then you plug everything in
Okay.
there, right? So you
I
just
just
kind of
wanna
go
make
back
sure
and substitute
Yeah,
those in.
that's-
All right, so there's a couple of things that, and I'm going to try to remember to write this on the board, leave this on the board, so you guys don't scream at me if I start erasing this. All right. So these are the elementary row operations for systems of equations. They're at the top of page 490. And they're numbered, but they're not numbered because you have to complete these in this order. You can do these in any order, you can do these multiple times. It's just here's what the possible basic row operations are. So we can interchange, and what we're trying to do is we're trying to put something in row echelon form. So here's the methods that we use to do that. We could interchange two equations. We could multiply one equation by a non-zero constant. And number 3, we could add a multiple of one equation to another. All right. So when we get to matrices, we're going to basically have the exact same steps, but we're going to swap out the word equation for the word row. And so the process is exactly the same. That's why I said what we're learning in this chapter, it's really the next chapter as well. We're just going to write it a little differently. All right? So the best way to understand what these mean is just to do an example. So we're going to do example 2. And you use this. This is used for what's referred to as Gaussian elimination. All right, so, you know, when we learned about solving equations in the last 2 sections, we used substitution. What were our 3 ways that we solved equations?
Substitution, graphing, and elimination.
That's right, substitution, graphing, and elimination. And so, hey, you were able to throw out one of those just before she got to it. So I'm going to give it to both of you guys. All right? But just a half point. All right, so this is elimination is what we're doing here. We're doing elimination, but we're doing it with 3 variables. Okay, and it's referred to as Gaussian elimination, and you'll use these operations to make it happen, just to start eliminating variables. So x minus 2y plus 3z equals 9 is our first equation. Negative x plus 3y plus z equals negative 2. 2x minus 5y plus 5z equals 17. All right, so here are our 3 equations, our system of equations. Equation 1, equation 2, equation 3. If it happened to be given to you not in this form, you're going to want to put it in this form where you put all of your variables, stick them in alphabetical order, and list them below one another. So you see, you know, all the x's are here, all the y's are here, and all the z's are here. Okay? I just say alphabetical order so you can keep track of them. So what we're going to do is we're going to use our row operations to try to start eliminating variables in here, so that we get something so that we get row echelon form. That's what we're going for. Okay. So we can interchange two equations. If it made sense for a different equation to be here at the top, we could swap their location. I don't think this example does any interchanging, but for some problems it might be simpler to interchange them. What we're going to do first is we're going to add a multiple of one equation to another. And in this case, the multiple is going to be 1. We don't actually have to multiply through. But we notice when we look at these two equations that if I add them together, what happens to the x variable?
It goes away.
It goes away, right? So we're going to add these together, and we're going to replace equation 2 with what we get. All right? These properties allow us to do that as we're doing Gaussian elimination. So we're going to go from here. We're going to add these two together, and so the first equation stays the same. We're going to put the result of the addition, we're going to list that now as the second equation. So when I add those together, the x's go away. Negative 2y plus 3y becomes just y, and 3z plus 1z becomes 4z, and 9 minus 2 becomes 7. So that's going to be our second equation now. Yeah, well, we could do multiple steps at the same time, but just for this one, so that I don't lose anybody, we're going to do one step at a time. All right. So what we did here, what did we do? We added equation 1 and equation 2, and replaced equation 2. So that was the steps that we took in order to do that. Right? Everybody see that? This is much easier to keep track of once you put it in matrix form, like to kind of summarize what you did. Notice even in the book they've got these big boxes here that say we did this and this is what we got. So that becomes easier with the matrix, or the matrices. So now the next thing we're going to do is we're going to add negative 2 times the first equation to the third equation, again to get rid of our x variable, right? Because ultimately, so we've gotten rid of one variable in this one, so this is looking like row echelon form, but we've got to still get rid of the x and the y variable in this one, right, to get row echelon form. So we're going to take the first equation and multiply it times negative 2, and then add that to the third equation to produce a new third equation. Okay? So, in other words, negative 2 times equation 1 plus equation 3, I don't know if I said 2 or 3, I meant to say 3, and to replace equation 3. That's what we're going to do in this step. Because again, those are all basic elementary row operations that we can do. We can multiply an equation by a non-zero constant, and then we can add the multiple of one equation to another. So multiply this through by negative 2. We're not touching this one, right? This one stays the same, so we can just go ahead and write all these down again. Why? Because they're already in the form that we need them. So we're just zeroing in on removing the x term from this one. So this equation here, if we multiply it through by 2, it becomes negative 2x plus 4y minus 6z equals negative 18. Does everybody see that? I'm just doing this step. Negative 2 times equation 1.
Why are you using negative 2?
Because I want to get rid of this. I'm going to take that and then add it to this to replace it.
The x's first.
Oh, okay. So you're just taking whatever the first thing of x is to multiply at the top to get rid of that.
Yeah, I'm multiplying the first equation by negative 2 so I can add it to this equation and then replace the result with this equation with that result. Okay? Yeah. So this is just temporary. We're not actually going to use that. We're not going to replace anything with that. We're just using it temporarily to add it to that so we can get rid of x. Okay? Yeah. So we add those together. The x goes away. 4 plus negative 5. 4y plus negative 5y becomes negative y. Negative 6 plus 5z is going to be negative z. And then negative 18 plus 17 equals negative 1. So that's going to be our equation. All right. All right. Then what we're going to do, I'm going to let everybody catch up with me. You guys there?
Are we gonna take the y and subtract it from?
So now these are already set up for us. We can add these together and replace the result, replace the third equation with the result, and the y variable goes away, right? And which will leave us with just z here, which is what we want. So let's do, so we're going equation 2, sorry, plus equation 3 to replace equation 3. All right, so that's going to be what we do next. So the top part becomes the same. I'm just going to put this over here so we'll have a little more room. X minus 2y plus 3z equals 9. The second equation stays the same because it's already like we want it, equals 7. And then when we add those two equations together, that last equation becomes, the y's go away, 4z minus z becomes 3z, and 7 minus 1 becomes 6. So we have 3z minus 6. So we're almost there, but the last thing we need to do to get this thing fully in row echelon form is what?
Get the z by itself.
Huh?
Get the z by itself.
We need the z all by itself. We got to solve for z. So notice when it's in row echelon form, all of these guys, the 1 is the coefficient on all these leading terms, right? So it should be 1x, 1y, and 1z as you go down each of the equations. So we're going to have, our final step is going to be, since the way the row operations are listed is we're multiplying by a non-zero constant, then we're going to say 1/3 times equation 3 to replace equation 3. All right, so our new version of it is x minus 2y plus 3z equals 9, y plus 4z equals 7, and then when we multiply through by 1/3, we get z equals 2 as our last equation. So now we have row echelon form. We've got a nice stair-step pattern. We've got a 1 in front of all the leading variables. 1 is the leading coefficient on all the starting variables. And now we're ready to do the back substitution and solve this one. But this is exactly the problem that we did last time, right? So the answer is going to be the same as we did in example 1. We didn't know how to go from this to this. So now you know how to do that using those row operations or equation operations. No, they call them row operations. All right. And that's definitely the term we use when we switch to matrices. Any questions about that?
When we are doing it on a quiz and stuff, do we need to write down what we're doing in each step or no?
No, I'm not really concerned about that. The benefit of writing down what you're doing in each step is I can kind of see maybe, if I know you're multiplying through by 1/3, I know you thought about this right, but if you make a math error here and come up with 1 instead of 2 or something, they'd be like, okay, that's just a count error, so I'm just going to count off a point. They still understood what the process was, I'm not sure how many problems we'll have like this though, because once we've switched to matrices, they're so much simpler to work with, and this is a lot of writing. There's a lot of room for error with this because you're having to write all the variables down. All the variables totally go away when you switch to a matrix. Yes?
You're telling us there's going to be less homework on 7.3 and just 7.4 because the matrices make more sense.
Yeah, 7.3 definitely. The homework's not as long as 7.3. All right? Okay, I don't want to run out of time, so just like we saw before when we were solving equations with only 2 variables in it, there's a possibility of, there are 3 possibilities when solving these things, and the possibilities are exactly the same. So we're going to write that down. 3 possible solutions, right? Number 1, there could be exactly 1 solution. Does anybody remember what we called that? I gave you a term that I said that you could use to, let me write the second one down. The second one is infinitely many solutions. And then the last possibility is that there's no solution. And so when I said there was no solution, we said we'd call that what? Does anybody remember the term, Diego?
Inconsistent.
Inconsistent, right. It's kind of like some of those basketball shots that I was witnessing Tuesday night. They were falling pretty good to start with, and then it went downhill from there. And I was sitting in the cavalry section because there was no room in the Kono section. So I'm listening. I'm surrounded by people cheering, right, as my team is losing. It was an interesting experience. So inconsistent. And I don't know if you remember, but we said both of these, when there is a solution, whether it's one or many, those are both consistent, right? But I want to give you another term so that you'll know you'll be able to distinguish these. So when there's exactly one solution, we say that that's independent. And when there are infinitely many solutions, if there's more than one, we say it's dependent. Okay? But just like before, both of these are consistent. So I could ask you that on a quiz or a test, right?
Yes.
Find the solution and tell me, is it independent or dependent? Is it consistent or inconsistent? So you got to know what those terms mean. So if you start solving equations, right? In the next example, you have a system of equations, and when you finally solve for z at the end of the equation, at the end of the process, z goes away, and you get something like this. If you end up with variables disappearing, and you get a statement that's not true, then that's number 3. There's no solution. All right? That's the same thing we saw before. You guys remember that? It's the same exact thing that we learned in the last section. The scenario where you have infinitely many solutions, what do you expect is going to happen when that's the case?
0 to 0.
The variables disappear, and you're left with some equation that is true, right? So if you get a true equation, it could be 2 equals 2. It could be any other number. But the variables go away, and you get a true statement at the end, and that means you've got infinitely many solutions. And for that scenario, I want to show you your answer is not simply there's infinitely many solutions. You need to be able to write an ordered triple with a variable in it that tells me what those infinitely so many solutions are. Okay, so let's see how you go about doing that. Everybody tracking with me so far, though? Are there any questions? Any questions about this over here? Possible number of solutions. So if you look at example 4, you see there as you start going through the equation operations, right? The row operations for systems of equations. What ends up happening is when you do that last step. So the second one where you had y minus z equals 0 and then 3y minus 3z equals 0. We're trying to get rid of y, and so we multiply the second equation by -3 and add it to the third equation, and when we do that, we get this true statement at the end there, which is 0 equals 0, right? And so that means that equation 3, then, is dependent on equations 1 and 2. That's why we say with the infinitely many solutions, it's a dependent solution, okay? And so what we're going to do in this one is, in order to figure out what the ordered triple would be for that, is we ended up being left with these 2 equations here. X plus y minus 3z equals -1, and y minus z equals 0. That was as simple as we could get it because the third equation disappeared. All right. And so what we're going to do is we're going to solve for since we know that this one here could be solved for y, and so then y equals z, right? Everybody see how I did that? Just solved for y there. So now we're going to take that and we're going to back substitute. So, I left my b out. Can't squeeze it in. Let's try that again. Back substitute. All right, into here. So when we do that, we get that x plus z equals y equals z minus 3z equals -1, and that means that x minus 2z equals -1, or x equals 2z minus 1. So that's just solving for x after we back substitute. And so in order to write our ordered triple, we're going to write an ordered triple based on this equation and this equation. But we can't use y or z in our ordered triple because all of our places in our ordered triple represent what x, y, and z should be. So we pick another variable, and we say that we just say that a is equal to z and y, right? So y equals z equals a, and we substitute in a for all of our values. And so when I do that, then this becomes x equals 2a minus 1. All right? And this becomes y equals a, and I could also say z equals a, right? So now we've got all of our x, y, z values. Our ordered triple would be 2a minus 1 for x, a for y, and a for z. It just worked out this time that y and z were the same. So when I plug in, and a just represents any real number. A is any real. And so there are infinitely many solutions, right? If I pick 1 as a value for a, I would get the three-dimensional coordinate 2 minus 1 is 1, 1 is a, and 1 is a here. So 1, 1, 1 is a possible solution to this, right? If I picked 2 for a, then 0 minus 1 is -1, 2, 2. That's another possible solution for this. So that's why there are infinitely many solutions based on the values that we choose for a. All of those would be possible solutions. I mean, I did that wrong. I'm sorry. I saw Adeline, saw her forehead go. It's like, you're totally wrong, but I don't want to sit at the desk of shame, so I'm not going to call them out. -1, 0, 0. Thank you. Thank you for speaking to me with your face. All right. Any questions about that? Very good? All right, cool. Let's see here. There are other solutions to this, by the way. They just kind of point that out. What if instead of using a for y or z, what if we instead had said that we were going to set x equal to b? If we had done that, because you may look at it and go, well, how do I know where am I going to plug in the a, right? If we had said x was equal to b, then we would have said that x equals b, and that would mean, like right here, b would equal 2z minus 1. And so if I solve for z, that z is equal to 2z, b plus 1 here, and then we multiply through by a half, and so z equals 1/2 b plus 1. And since z is equal to a, I could have had something that looked like this. I could have said my equation, my ordered triple was b, comma, 1/2 b plus 1, and then the z term would have been 1/2 b plus 1 as well. So that, what if I'd gone that route and said that's what my ordered triple is? This still works, right? If I plug in 1 here for b, I still get 1, comma, 1, comma, 1. It'll still work out the same as you plug in values for b instead of a. So your solution here could look a little different than my solution, depending on which term you decide to make your variable. Okay, which variable you replace with a or b or whatever other variable you want to use. I would stick with a, simply. Okay, did I lose anybody when I did that? I just want you to see that, this makes it harder for me with grading this stuff, because yours may look a little different than mine does. But it's usually easier to take the simplest one, right? If you've got one that's just something all by itself, set that one to your other variable, and then just solve the rest of the equations based on that. Okay. So just notice right here what we ended up with was two equations, and if you have a system of equations where you've got less equations than you have variables, which is what we have here, we only have two equations, but we've got three variables. You know right up front, if that's the case, you're not going to be able to solve this and get like numeric answers for all of the variables. So anytime you've got this scenario here, you're gonna end up with this infinitely many solutions, right? You're gonna have a dependent situation there, where you're gonna end up with something with an A or something like that in it. So that's what example 5 is. They're just kind of showing you that will happen. All right, but we need to go on and talk about matrices. So let's go to the next section. You guys have never had matrices before, right? This is a new concept. You're going to see, it's going to be very familiar. You're going to see it's the same stuff we've been doing. You're just going to go, huh? You're going to be like, this is so much easier to work with. It's just neater. The other one gets it gets complicated. So, so these are matrices, or that's the plural form, right? Singular, or a matrix is singular. All right, so let's just define what a matrix is. Definition of matrix. It is. Well, let me tell you what it's not. It is not a simulated reality. All right, so if you've seen those movies, I don't want you to get confused. Right? This is the way we need to think about it. If m and n are positive integers, the m by n matrix, and that's how we read that m where we got the little multiplication sign between it. Just like you'd say the measurements of a room were 11 feet by 12 feet or something like that, right? So we read that m by n. The m by n matrix is a rectangular array, and it looks like this. So we got A11, A12, A13, dot, 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 all the way to A1n, and A21, A22, A23. This is kind of weird writing it down. It's going to be a lot simpler when we actually do one. But dot, 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 we can go down from there and say finally it's a M1, a M2, a M3, dot, 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 a M, So that's what the full matrix looks like. This is row 1, this is row 2, this is row 3, this is column 1, column 2, column 3, this is column N. I did this wrong. This row 1, row 2, and then row M. So it's set up like this, where each entry, that's the language we use to speak about each individual number in here, represented by this variable A11 or whatever. Each entry, A, which is in the form Aij, is a real number. And M by N matrix has M rows and N columns. All right, so that's a confusing definition, but I'll just let you jot that down. It will explain what we mean by that, and it'll be much simpler once we do an example. me define dimension. If I asked you what the dimension was of this matrix, the dimension is m by n. So when we say m by n, that is what the dimension refers to. And so if m equals n, it's a square, so have a square matrix. That should make sense. If it's the same number of columns as rows, then it would be a square matrix. And the main, what we refer to as the main diagonal, move this out of your way. The main diagonal entries are A11, comma A22, comma A33, dot, dot, dot. So just as you're thinking through that, how the numbers would work out if it was a square. They just made that note. But like I said, this is all kind of fuzzy stuff until you do an example. But I do want us to look, once you get finished there, I want you to look at example 1. Don't look at the answers to example 1, but we're just going to, based on this definition here, we're going to give the dimension of each of the matrices that are listed. All right? I don't want to write that down for time's sake, so you guys just look at it with me when you're done. So we're looking at example 1 on page 504. We're looking at A right now, which is, I'll write this one down because it's so simple. The A is just simply this matrix here. All right? Just a single number all by itself. So what would somebody that's not on the board want to take a stab at that one? What would the dimensions be for that? How many? We always put, when we're listing it, remember, m is the number of rows, so we put the rows first, so it's always number of rows by number of columns. So how many rows do we have for that one?
1.
Just 1, right? So what would based on the number of columns, what would the dimension be for that one, Sean?
1 by 1.
It's just a 1 by 1, right? It's 1 by 1. So that way, if I asked you for the dimension, that's what you would put. Okay? The next one, there's only 1 row, but there are 3 columns, right? Oh, there's 4. Sorry. That little half jumped there next to the 0. I missed that. So there's 3 columns, so it would be a 1 by 4, right? The next one. We have a square matrix
2 by 2.
for C, so it would be a 2 by 2, right? The hardest thing is just remember, do you put the rows or the columns first? So make sure you know that. That's actually going to be critical when we start doing operations where we're like multiplying matrices together or adding them together, stuff like that. It's going to matter that you understand that it's rows first and then columns. So D would be what? Dimensions for D in the book?
2 by 3.
No, it's 3 by 2.
3 by 2. You got to put the rows first. There you go. Come on, dude.
Oh,
Yeah. 3 by 2, and then what's E? Let's make sure Hayden has it. What's E, Hayden?
3 by 1.
3 by 1, exactly. Yeah, put your rows first. All right. I'll tell you, that's the trickiest part.
Yeah, I just read it.
Is putting the rows first. All right, so let's talk about how you can write. How do you take a system of equations like we had before and translate that into a matrix? All right. So let's do that. If I have system of equations like we had before, so we've got x minus 4y plus 3z equals 5, negative x plus 3y minus z equals negative 3, 2x. We don't have a y term, so we're going to leave an open spot right here as we write our equations down and put the negative 4z over here equals 6. So there's basically 3 matrices I could ask you for that come from this system of linear equations. And so all you do is you just take the coefficients of each variable and you write those down. And if there's not a variable there, you don't leave a blank on the matrix, you put a 0 where that variable is missing. So it would look like this. The first matrices you could write would include all of that information. So we just take the coefficients from the first one, 1, -4, 3. Does everybody see where I got this? Just as the coefficient of the x term, the y term, and the z term in that top equation, right? This one, we're going to include what the constant values are on the other side of the equal sign here, but we want to identify that as constant values that don't have a variable, so we're going to put a line. They do a dotted line in the book. I've seen it more like this. It's just easier to see on paper. So you just put a straight line here, and you put your 5 out here like this, and we're going to close off the matrix there. And so we're going to do the same thing for the next row, -1, 3, -1, -3, and then finally 2. We don't have a y term in this third equation here, so we're going to put a 0 in that column. -4, 6. And we call this an augmented matrix. So if I ask you to write the augmented matrix for a system of equations, that includes every number that's in your original system, right? Including those constant values. We call that an augmented matrix. So you always have this line here so that you can tell where the constant values are. Now another type of matrix I may ask you that I may ask you for is the coefficient matrix, which only looks at this portion of it. It doesn't look at anything to the right of the equal sign. It only looks at the stuff with variables to the left. So that would be 1, 4, 3, -1, 3, -1, 2, 0, 4. So just the stuff that's to the left of our line here. And that's a coefficient matrix. And then finally, I might ask you for the constant matrix, which is just the constants that are to the right of the equal sign. So just the 5, -3, 6 would be our constant matrix. So understand those terms and make sure you know what we're asking for. If the directions said, give me that particular matrix. Yes?
The coefficient matrix is the 4 negative.
It is. Yeah, I was hoping you would catch that. So good job. Good job. Thank you. Sean is exactly right. So that's the hard part with the matrix, right? You just gotta. There are a lot of numbers, and when you're copying them down like this from this equation, or just moving stuff around, it can be easy to drop a sign accidentally or do your math wrong when you're doing row operations and things like that. So you gotta take your time, be careful. So I told you I left this up on the board because when we're working with matrices, the elementary row operations for matrices. I'm sorry, I'm not going to have time for you two because you can't do what I just did where you just erase it, right? I'm not going to have. You might want to just say in your notes, hey, make sure you copy those down or realize that it's the same. But basically, everything where we've got equations in here, we're going to replace that by the word row. Or rows. So interchange 2 rows, multiply 1 row by a non-zero constant, add a multiple of 1 row to another. Okay? So it's exactly the same steps that we learned in the last section. It's just since we're dealing with matrices and the term equation doesn't make sense, we're just talking about rows here. Okay? So the thing that we did with Gaussian elimination and back substitution for solving an equation. Let's see how we would go about doing that for using matrices. All right. And we've got a system of linear equations that look like this: x minus 2y plus 3z equals 9. Negative x plus 3y plus z equals -2. And then 2x minus 5y plus 5z equals 17. And so we want to do the same thing we did before, but this time we're going to use a matrix to do it. So we're going to write down the augmented matrix to this system of equations, all right? So what would my augmented matrix be?
1,
1,
negative
-2,
3,
3, put a line,
9,
9, right? -1, 3, 1, -2, 2, -5, 5, 17. Right? Super simple. And we think of these, this is row 1, this is row 2, this is row 3. Right? So what we're trying to do is we're trying to do the same row echelon form that we learned in the same chapter. But when you do that in a matrix, what's going to happen is that you're going to get ones down this diagonal right here. And everything that's to the left of the ones are going to be zeros. Because that's where the missing variables are going to be that were in the last section. Okay? So if that doesn't make sense to you, it should make more sense as we move forward. But you're looking for the same patterns. It's like, can I multiply and then add to get rid of something? So the first thing I'm going to target is I want this to be a 0. Right? Basically, I need this to be a 0 and this to be a 1, and I need this to be a 0 and a 0 and a 1 right there. That's what I'm trying to do. And so we're going to start right here. Let's get rid of that -1 and make it a 0. And all I've got to do in that case, let me erase these so they don't confuse us as we move forward. All I've got to do in that case is just add those two together and replace the second row, right, with the result. And so I'm going to, right here, I'm going to say row 1 plus row 2 equals row 2. All right, I'm going to add row 1 and row 2 together to create a new row 2. All right, so my matrix is going to be same thing on the top. I didn't touch that. Right. The bottom though, when I add them together, 1 plus -1 gives me a 0 here. -2 plus 3 gives me a 1 here. 3 plus 1 gives me a 4 here. 9 minus 2 gives me a 7 here. I haven't done anything with row 3 yet, so we're just going to leave that alone. Okay, isn't that much easier to write down than what we did before? Much easier. Now, when I did that, I kind of got the 1 here for free, right? I was just trying to get a 0 on that first term, but a 1 showed up here, so I'm actually good on this second row.
What would you do if it didn't show up?
I'd have to multiply through by some fraction, right? Like this, if this had been a 2, I'd multiply the whole row by a half.
A half, okay.
Okay? So now, we need to get rid of this 2 here, so we're going to start with that first. Obviously, I can't multiply row 2 by anything and add it together because there's a 0 there, so I'm going to have to focus on row 1. So what I'm going to do is I'm going to take row 1, multiply it times -2, -2 row 1 plus row 3, and I'm going to replace, as a subscript, let me rewrite that. I'm going to replace row 3 with that, right?
And we're multiplying by -2 so we can get rid of the 2 on row 3, right?
That's right. That's what I'm doing, all right? So that is going to look like, same thing on the top, -2, 3, 9, none of that changes. 0, we're not touching row 2 because row 2 is already in good shape. So 2 times this top row here and add it to -2 times the top row and add it together is going to give me a 0 here. -2 times a -2 is a +4. -5 is going to give me a -1 there. -2 times +3 is -6. Plus 5 is going to give me a -1 there. And then -2 times 9 is -18, plus 17 is going to give me a -1 there. So that's what I've got so far. Have I lost anybody along the way? Is everybody tracking with me? Everybody good? All right, so now on this bottom row here, I need to get rid of this -1, right? I need a 0 there. And so these equations are already set up for us. We just add those together. If these equations hadn't been set up for us though, we definitely want to use row 2, because if I added anything from row 1 to this equation, this first value is going to change from being 0, right? So these are the 2 equations that I want to focus on now at this point.
And then the same thing, if it wasn't set up where we could get the 1 to equal 0 in row 3, the -1 to equal 0 in row 3, we just multiply through with the fraction again.
That's right. That's right. Yep. So we're going to do this step. Row 2 plus row 3 equals row 3. All right. So we've got top stays the same, Second row stays the same because it's already in good shape. Third row becomes 0, 0 as we add row 2 and 3 together. 1 minus 1 is 0, 4 minus 3 is 3, and then 7 minus 1 is 6. So that's our new matrix. We're almost there. What's the last thing we've got to do?
Divide. Or to go to a
Really
fraction.
multiply through by a fraction, right? Or but divide, however you want to think about it. Divide by 3 and multiply through by 1/3. It's easier to write down on our little arrows here if we say it like this. 1/3 times row 3 is going to equal row 3, right? So we multiply row 3 by 1/3 to make this 3 right here at 1. So our final matrix that's put in row echelon form is going to be this one right here. It looks like that. Now we're not. I'm sorry, I didn't. I didn't do it. 1/3 times 3 is 1, and this becomes a 2. There we go. So we're not done yet, though, because our job was to solve this system of linear equations, right? We're supposed to end up with an answer that's an ordered triple, and so we're not there yet. But what we've basically done with these row operations on the matrix is now we can pull from this a new set of a new system of linear equations, which is in row echelon form, like we learned in the last chapter. So we can say for that first row, x minus 2y plus 3z equals 9, y plus 4 equals 7, and then z. Oops, 4z, my bad. And then on that last one, z equals 2, right?
So by getting everything to equal 1, we just know that it can equal the variables x, y, and z.
Yeah, so this is our x column, this is our
Yeah,
y
yeah.
column, this is our z column.
Okay.
Right? This is our constant column. And so now we're doing the same thing we did before. We just take the z, plug it back in, and then once we solve for y, we plug y and z into that first equation, and we get an ordered triple, which is 1, comma, -1, comma 2. That would be the answer for this system, the solution for this system of equation. Remember, just like we did last week, we don't have time in here to do it, but you really, to make sure you got it right, you should take the x, y, z and plug it into the previous equations and make sure that you get true statements. Okay, so let me define, or I'll do that here. I need to define, we've talked about row echelon form, but we haven't given you a specific definition for that. So, row echelon form, and what we call reduced row echelon form. If matrix is in row echelon form, right, then this will be true. Any rows with only zeros will be at the bottom of the matrix. So if we happen to, while we were doing this, all of our variables disappeared, we got zeros, then we need to make sure those rows are at the bottom of our matrix. And it's okay for us to do that because step 1 in our row operations is you can swap out rows. You can interchange 2 rows. The next thing is if not all zeros, if your row is not all zeros, first non-zero entry is 1, right? We call that term the leading one for that row. And then number 3, for it to be in row echelon form, for 2 successive non-zero rows, leading one in higher row is farther left than in row below. Right? That's just we're describing with words that stair-step pattern that we see where those leading ones are to the left of one another as you kind of go up the matrix. So hopefully as you see that none of those are surprising, those are just things that we've already, as we've put it in row echelon form, it's like, okay, that makes sense. Maybe the first one where you have rows with only zeros, we haven't run into that yet, but just make sure you know those are at the bottom. Now, if is in reduced row echelon, form, each leading one will have only zeros above and below it. All right, so for that last point, just to make sure we're clear on that, this matrix would have had to look like this. The matrix as it was in row echelon form, but to be in reduced row echelon form, it would have to look like that. Does that make sense? Now, if it's in reduced row echelon form, what just happened? If you think about what those columns representing X, Y, and Z, we just solved for X, Y, and Z, right? We never had to go back here and do the back substitution. We could just go directly from this and say that our ordered triple is 9, 7, 2. You guys see that? So if you can use those steps to make it look like that, you've actually solved the whole thing just using the matrix without having to do the back substitution. Okay? So we've already done these things. What you call this here when you get it in this form, this is when you use what's referred to not just Gaussian elimination, but it's called Gauss-Jordan elimination. Gauss was the older dude and Jordan was the newer dude, right? So Gaussian elimination was around for a while, then Jordan came along and said, hey, if we do this right here, we can just solve the whole thing, inside the matrix, which is not virtual reality environment. Okay? I don't want you guys to get confused with that. So you're going to see that term Gauss-Jordan elimination in your homework, and so I don't want you to be confused by that. We're out of time, so I don't want to take up your lunch portion, but I do want you guys to look at 2 things in the book on your own. Okay? So on page 510, example 7 shows you what will happen if you have a scenario where there's a system with no solution. All right? And if you just glance at that real quick, you'll see as we were doing the row operations on our matrix, the third row became 0, 0, 0 with a -2 at the end. And so that means that the third row turned into this, 0 equals -2. It's just the same thing we saw before. There's no solution if you, yes?
If it was like 0, 0, 0 and the -2 was also 0, you would just move that to the bottom.
If it was 0, 0, 0, you would move that to the bottom, and in that case that's the scenario where, Let's go see. Well, they don't. But if that had happened, you would be in the infinitely many solutions category, right? Because you would get a true statement at the end, 0 equals 0. Make sense? But the infinite solution example is example 9. It doesn't work out like what we just described, Diego, but it's a scenario where you've only got 2 equations, but you've got 3 variables. So that one's going to have infinitely many solutions. And you just do the same thing that we did before. You have to pull out of the matrix the final system of equations and then put a variable a in there and come up with the solution based on that. Okay? All right. Like I said, reach out if you've got any questions, and you guys have a good day.